So in addition to the cycloaddition video that we have that I've already shown you, let's look a little bit more and work through some sample problems and see if we can come up with the solutions. So here we're going to look at some sample problems out of the chapter. We're going to talk for a few minutes about stereospecificity, retrosynthesis, which means just working backwards from the product back to the starting diene and dienophile, and we're going to look at some 3D visualization of the bicyclic compounds. Alright, so remember with the Diels-Alder, here's the mechanism. We have a pair of electrons coming here, a pair of electrons from this pi bond coming here, and this pair of electrons being shifted to here. Right? And so what these arrows indicate is that you're going to have a new sigma bond here, a new sigma bond here, and a new pi bond here. In the product we get this cyclohexene derivative shown here. Remember the mechanism is pericyclic, it's concerted, and it goes through a cyclic transition state. So let's look at a couple of examples here where it says draw the product. Alright, so let's look at this first example. I think the key to these problems is to understand the arrow pushing and the mechanism. Alright, so what you want to do is look at the problem, find the diene, find the dienophile, and if once you have identified your two substrates, then put the arrows in. Right, so let's do the arrows for this first problem. Notice I have an arrow coming here from the diene to the dienophile. I have an arrow coming here from the dienophile to the diene, and then this double bond here in blue with the blue arrow, that's the double bond that's going to get shifted up. So I'll give you a couple of seconds to think about it and draw the product starting now. Okay, stop. Let's see what we have. Alright, if you have this as a product, then you're correct. I have the stereochemistry shown, and I'm going to talk about that in a minute, but just to remember that this is a stereo-specific reaction. So this cis double bond, those substituents have to remain cis in the product. So let's look at the next one. Alright, so here's my diene, here's my dienophile. I'm going to actually rotate that dienophile around to make it vertical so that it'll be easier for you to put your arrows in. Alright, so let's put the arrows in. Alright, think about it for a second. And here is the product. Notice this is a trans double bond, and so these two substituents here in the product have to be trans because again this reaction is stereospecific. Let's look at the last problem. You have your diene here, you have maleic anhydride as your dienophile here, and let's see what we get from here. Right, here are my arrows. Remember this arrow is indicating that I'm making a sigma bond here. This arrow indicates that I'm using these pi electrons to make a sigma bond here, and then this blue arrow just indicates that this pi bond is being shifted over. So what's the product? I'll give you 10 seconds. Alright, so this is your product. Alright, for all three of these, I could draw the other stereoisomer where this would be wedged and that would be wedged. These two would be wedged, and also this would be wedged and this would be dashed. So you should practice drawing that because it is possible to get the other stereoisomers that are here. And so what I would like for you to do is just try this out. Just try drawing the other stereoisomers. Again, if both of these are wedged, that's still cis. It's just a different stereoisomer. If both of these are wedged, it's still cis. It's just a different stereoisomer. And then try drawing the other stereoisomer for this product right here. Alright, so again, this is a stereospecific reaction. If I start with a cis double bond, then those substituents have to be cis in the product. If I start with a trans double bond, then those substituents have to be trans in the product. Alright, so how do we know, let's say for instance if the double bond is cis, how do we know if the substituents get pushed up or wedged or get pushed down, meaning they'll be dashed? Alright, so the answer to that is to understand how the diene approaches the dienophile. So if the diene approaches the dienophile from the top, then you can see here, this is the diene here, and then this is my dienophile. Okay, so this is the alkene, the double bond. So if it attacks here, then obviously the groups are here attached to the dienophile are going to get pushed down, right? So those will be on a dash. If it attacks here from the bottom face, then what you'll notice is that the groups on the dienophile should get pushed up, which would mean they would be on a wedge. And so that's just a way to think about this. I know it seems like a lot, and I don't expect you to grasp it right away, but with practice you can really grasp this and you can really understand it. So what happens if we use a triple bond as a dienophile? Well, the triple bond is made up of a 1 sigma and 2 pi bonds, but when it reacts as a dienophile, only one of the pi bonds is actually going to be used. All right, so the alkyne is only going to use one of its pi bonds if it's being used as a dienophile. So let's look at what the LUMO would look like, because again, it's the HOMO of the diene and the LUMO of the dienophile, and I couldn't get my software to show both lobes at the same time, but this would be above and below here, and then the other pi bond would be like this, where one side is coming out of the screen at you and one side is going back into the screen. But again, only one of those pi bond LUMO molecular orbitals is going to react or going to interact with the diene. And so let's look at some examples. So here is my diene. My dienophile is an alkyne. So here are my arrows, and I'll show you this product here. Right? Notice only one of the pi bonds got used from the alkyne. The other pi bond is still intact, so I still have a pi bond here in the product. All right, let's look at another example. Here's my diene. Here's my dienophile. Okay, let's think about it for a second. I'll put the arrows in, and I'll give you 10 seconds to draw the product. Alright, so here is what that product would look like. Right, you have a sigma bond here, a sigma bond here, pi bond gets shifted here. Only one of these pi bonds gets used, and so the other pi bond is still intact. Alright, let's look at a third example. And with this example, we have here's our diene, here's our dienophile. Alright, 10 seconds, go. Alright, stop, and hopefully this is the product that you got. Again, I have a triple bond, but only one of the pi bonds gets used, and so that's where this other pi bond from the triple bond is still intact. Alright, so we'll pick this up. I'll do more of this in class, and I'm going to have a second video that I'm going to send out, but we won't cover that video on tomorrow. This is what we're going to cover on tomorrow. All right, thanks.